power and energy. Now, this is the largest unit on the AP test. This makes up to about 25% of the test. So if you only have, ooh, hang on, do we have good audio here? I suppose. Goodness me. There's just clutter going everywhere. Okay, how about let's do a real quick test to make sure our audio is going to work out before I get too far into today's topics. I'd hate to start speaking for a very long time and then realize halfway through that no one could hear me properly anyway. Here we go. Just want to double check here. Okay, so I can hear my own voice. Alright, and now we're gonna get rid of that because otherwise we're gonna get a weird echo and I don't want to deal with that. Yeah, so today we're working with conservation of energy. So energy conserved in closed systems, and then if there's open systems, energy being added to a system by work, and then the kind of time component to that, which would be work per time, which is power. Yeah, and so I figured for, excuse me, once again, we will also have our chat window up here for both YouTube and Twitch. So if any messages, if you're ever confused about something I do or you have any questions, feel free to type out a message. Whenever I look to this way, that means I'm just checking the chat. So I'll be doing this periodically as we go. I figure for this time, we'll actually start by just going over some of the topics a little bit more generally first, before we delve into practice multiple choice problems and then practice FRQs like usual. Right off the bat, we're going to be dealing with energy. And so energy we can quantify in this level in two different types. That will be kinetic for objects in motion and potential. And I also am going to need to make sure I've got my dead zones correctly and make sure that I'm not writing where something is going to be covering it up on the screen. But it looks like we're good so far. That's what I'll be doing if I check over there too. And so our kinetic energy we can model as 1/2 times our mass times our velocity squared. Notice how when we square this velocity, this no longer applies a direction to it, because if it's a negative direction, the -1 squared just gives us a +1. Meaning that these are all scalar quantities. These are not vector quantities like velocity would be. And then potential has a few different forms based on what the potential is coming from. Technically, we can derive this from a potential field and consider ourselves moving through a potential field to a lower potential. But this would be something that's difficult to describe without using the language of calculus, which is not what we're going to be doing at the AP Physics 1 level here. And so the main types of potential energy we're going to concern ourselves with is going to be the gravitational potential energy, which is mgh for almost all of our purposes. But in the larger case, we can also use the big G gravity for gmm over r. Notice how it's r instead of r squared for potential. R squared would be the gravitational force. And then the other potential we'll see is spring potential. And this will be 1/2 kx squared, where k is our spring constant, as used in Hooke's law, and x will be our displacement from the resting position of the spring, from the equilibrium point. And that can go either direction. We can compress a spring and it's going to gain some potential, or we can stretch a spring and it still gains that same potential. And so we expect our total energy to equal the sum of our kinetic plus our potential. And so we can then look for specific times where maybe we're interested in a time where we start out at rest, and so our kinetic goes to 0. Or we start out from the bottom of a hill, so our potential starts at 0, but maybe we climb up. We'll be looking for these different cases to make our equations a little bit simpler. But in the broadest strokes, we expect energy to be conserved inside of a system. So inside of a closed system, this tells us that our final energy has to equal our initial energy. This is for a closed system. And then what that looks like then is that tells us that our final kinetic energy plus our final potential energy is equal to our initial kinetic energy plus our initial potential energy. Now, this is good for conserved systems where we are accounting for everything that's already in the system and we're not adding in or taking out any other energy. We're just looking at energy changing forms between potential to kinetic and back and forth. But we will deal with some, so yeah, I guess let's write this as, make a little note, say this is for a closed system. But for an open system, we have influences from the outside. And our conservation of energy takes a slight turn, not a big twist, but we expect our final energy to equal our initial energy like before, but now we're going to add a plus W term. Now this W is going to be work. And so work done by a force is proportional to that force times the distance that it travels. But if this force and distance are not aligned, because these are vector quantities, if they have some sort of angle between them, we have to take the cosine of that angle between them to take the piece that is aligned in these cases here. And so what we see here for this conservation of energy equation, we're really saying our total energy in the system at the end. So this final energy here is equal to the energy we started with plus the energy that we put in. Bear in mind, this can also be a negative value, so that would then mean minus the energy that we took out. Something like friction does this, right? This pulls energy out of a system, which it technically then goes to release as probably thermal energy or energy further down different ladders, but yeah, we don't need to worry about that too much. And then our last piece that we're gonna concern ourselves with is gonna be power. Now, power is gonna just refer to the change in work or the change in energy. So the work being done divided by the time. And technically, we can include a delta t because this is like the amount of time that this work occurs. And so if it's in a fixed time zone, we only want that little amount of time where the change was occurring. And so, yeah, and I guess we can also, from this equation here, we can rearrange, if we minus initial energy from both sides, we get EF minus EI is equal to work. And EF minus EI, that's just our change in energy. And so this gives us any change in our total energy has to be done by an outside force, is work done by this outside force. And so that's another way we'll be able to deduce work. We'll see that come up in some of the problems. So far, so good. Looks pretty good. Why don't we move on to some multiple choices here and see some of these in action? All right. So right off the bat, we're actually dealing with a simple harmonics problem. We'll see this again in a couple weeks or next week because this is an important equation for simple harmonic motion. But so we're asked for a mass on a spring with mass m and spring constant k set in simple harmonic motion, so it's oscillating back and forth. We maximum displace it from the maximum displacement from its equilibrium position is a, so that's the amplitude of our wave, if you prefer. What is the mass's speed as it passes through the equilibrium position? So for this, we can use conservation of energy. So at its maximum displacement, we expect all of its energy to be in potential energy. This is spring potential, which would be 1/2 kx squared, but our x is a distance a, because that is our amplitude. And so we expect this total amount of energy at that displacement to equal the energy when we go through the equilibrium. Once we go through the equilibrium, that is when the spring's displacement is 0. So our x goes to 0, there's no more spring potential, all of our energy is in kinetic. So we can compare this to our kinetic energy. And there's our velocity term. That's got the mass's speed encoded in it. So we can multiply both sides by 2. We'll divide both sides by m. And we get v squared is equal to k over m times a squared. And we'll take the square root of both sides. And square root of a squared we can pull out front to write as a times the square root of k over m. So just using our conservation going from potential energy to kinetic energy, we got option B here. We'll talk about this a little bit more in a week. There's some nice corollaries we can do with these types of a problem. We'll probably see that one again. Next, we've got force F at some angle theta above the horizontal is used to pull a heavy suitcase a distance of weight mg a distance of d along a level floor at constant velocity. Coefficient of friction between the floor and the suitcase is mu, so then the work done by the frictional force is going to be best described as which one of these. So we've got an object, and we're lifting it up at an angle. Now this angle is going to actually prove to be a little bit tricky here, because what this does is this changes our normal force. We have, I guess I probably shouldn't have drawn it that way. Can I squeeze that out? So we have this as a y component and an x component of our forces, right? This was our force of magnitude F. This is some angle theta. And this x component is the one doing the work to bring us forwards. And then we also expect to have a frictional force pulling us backwards, doing work to pull energy out of the system. And then we have a gravity force and a normal force. And so we have that as Fn, and then this is Fg. And so normally we would calculate friction force by finding mu times our normal force. But in order to do that, we'd have to find the normal force, which would take this vertical piece into account here. This y component is reducing our normal force, and we don't have a good metric on that. So what we can do, though, is we can also use the condition they say that we are traveling at a constant velocity. So constant velocity, what does that mean for us? Well, that means our acceleration in the x direction is going to be 0. So that tells us that this x component of our frictional, or the x component of our pulling force, excuse me, is going to equal our frictional force. And so we can get this x component as going to be, so f of x over f, that's the adjacent over the hypotenuse, so that's the cosine relation. So we can bring that through to as f times the cosine of theta. And we expect this to be equal to our friction force due to Newton's second law, from the case that fx minus ff is equal to 0. Am I blocking this? Oh, I'm blocking it a little. Okay. Can I bring that back over? I kind of can't. Okay, and the mic's being really weird. Okay, I think the mic, does that work? Okay, I think we're good. Okay, but yeah, this is equal to 0. So yeah, I mean, you can kind of see that on the edge. I'm not going to change it. We'll get the square root a little lower. Can you see that? Not really. Okay, yeah, I kind of just picked a bad spot to start writing, I suppose. Okay, at least we can see all the problems, so there's that. Yeah, and then the work done by this is going to equal the force times the distance times the cosine. And our distance is going this way, or our displacement, moreover. And so FF is opposite that, so that's going to be 180 degrees over. So cosine of 180 degrees is -1, giving us the work done as equal to a negative F cosine, yeah, FD cosine theta. I guess, yeah, I should be careful here because this is a different cosine theta. We'll call this one like cosine phi or something. But that cosine phi gives us the -1, and this gives us letter A is our answer here. Good, good. Do we need, we don't even need the mu for that, do we? Yep, that's a little strange. So we were given the coefficient of friction, but I think that was just a non sequitur. Ooh, 3 is a kind of a tricky one here. Because we've got a 2 kilogram ball is attached to an 0.8 meter string and whirled in a horizontal circle at a constant speed of 6 meters per second. The work done on the ball during each revolution is going to be equal to which? Now, a ball traveling in a circle, if you remember from last time, we did centripetal forces, right? And centripetal forces would be the force accelerating. This would be the force that would be doing the work. And those are going to be pointing radially inwards. So for ball and a string, this would be a tension force. But our motion is always going to be perpendicular. We're always moving around this way, and the cosine of 90 degrees goes to 0. So we expect at any given point on this circle, the displacement vector to be perpendicular to our force vector, meaning our work goes down to 0 in that case. So that means D is going to be our answer for number 3. Good. So 4, we've got a pendulum with a bob of mass m. Bob is the name for the little thing at the bottom of the pendulum. On a cord of length L. It's pulled sideways until the cord makes some angle theta. And the change in potential energy of the bob during the displacement. Okay, so we want to find the potential energy after we lift it up some angle theta. Do I have space down here? I've got a little space down here. We might need to get a new page as we go. Yeah, I'm gonna do that now. Oops, we don't want to skip ahead. Let's add a page. Here we go. And I'm gonna make it a scratch paper page because I kind of like these. So we want to know if we have, is this a good spot to draw? Yeah, it's a good spot to draw. So if we have some pendulum here with mass m, and it wants to sit there, we know this side is length L, and this total length is length L here. And this is enclosed by some angle theta. Now, what we can do is we can take our new height and see where this intersects. And so, now we've got a right triangle, because this meets at a perpendicular, and this length, so we have the distance we've displaced this by, we've raised up our bob by a height h. And we can solve our potential energy as we're looking for something of the form mgh. So we need to get a way to express h in terms of L and theta. And so what we can do is we can use this upper end. This is going to be L minus h. And that's adjacent to our angle, and our hypotenuse is L. So that means our cosine relationship is going to be our adjacent, so that's L minus h, over our hypotenuse, which is L. Giving us then, if we multiply both sides by L, L cosine theta is equal to L minus h. And we want to get h on its own, so I'm going to actually add h to both sides and then minus L cosine theta, giving us h is equal to L minus L cosine theta. And now we want for our u to equal mgh. This is going to equal mg L minus L cosine theta. I think someone texted me and it made an interference pattern. Now my microphone doesn't want to play nicely. Come on. Is it going to work? I think it's going to work. Okay, sorry about the technical difficulties there. And we can factor out this L too. We can write this as mgL times 1 minus cosine theta. And let's see. That's letter A. Look at that. Very cool. Any questions on how we did that? Doesn't look like it. Cool, cool. Let's just keep on trucking. So we've got a softball player who catches a ball of mass m, which is moving towards her with some initial velocity v. While bringing the ball to rest, her hand moves back a distance d. If we assume constant deceleration, the force exerted on the ball by her hand is going to be what? So what we can do is we can compare all the initial kinetic energy that this ball had, which would be equal to 1/2 mv squared, to the work done that it took to bring it to rest. And the work done would be the average force she used times the distance she traveled. Her hand moved. And so we're looking for the force. We're just going to divide both sides by d, giving us F is equal to mv squared over 2d, which is A again. Very cool. Alrighty. No questions? No questions. You guys are great listeners. So next we've got a pendulum is pulled to one side and then released. It swings freely to the opposite side and then stops. Which of the following might best represent graphs of kinetic energy and potential energy, and then the total mechanical energy? So we expect total mechanical energy to be constant for each. This is a little tricky to see, so here's what I'm gonna do. I'm gonna circle in red the kinetics, and I'm gonna circle in green the potentials, just so we can see better what these graphs are telling us. So we're looking for a case. It pulls up to one side and released. We expect all of our energy to start in potential energy. And we see at the beginning, for this one, we start with 0 potential. This one we start with positive. This one we also, oh, no, that one we don't start with positive. We start with that down there, my bad. This one we start with a positive potential energy. And then the last one we start with a negative. And so right off the bat, that actually rules out 3 of them. That rules out this one, that rules out this one, and this one. And so we can still see, so our answer is going to be C, but we can also see this behavior and see how it mirrors what a pendulum is going to do. We're going to start in potential energy, and as it swings down, this potential reaches 0. That's going to be at this point of maximum speed, maximum velocity, highest kinetic energy. And that's what we see happening here with this red line. It's going to be kind of coming up, maxes out when that hits a minimum, and then we start going back up again, and we're picking up more potential energy as we're converting back that kinetic energy, which then starts dropping. And then the total on the top is the sum of the two. We expect that to stay constant because there's no outside forces influencing this, so we expect our energy to be conserved. Good, good. So 7 and 8, we're looking at a car with mass m sliding across a patch of ice at some speed v with its brakes locked. It hits the dry pavement and skids to a stop in a distance d. The coefficient of friction between the tires and the dry road is given as mu. So if we doubled the mass, it would have skidded a distance of what? So we can compare this. This is actually going to be the same relation we have up here. We have some initial kinetic energy that we are bringing to rest as we bring the car to stop. And we're doing that by doing work on the car. And that's going to be, this force is a force of friction that does this. And so, let's see, we just want to see how the mass changes this. And so we have 1/2 mv squared is equal to, this would be mu times mg times d. And then we want to see what happens if we double the mass. And if we double the mass, it actually doubles both sides. Because if this goes to 2m, we get another factor of 2m over here. Meaning that d actually doesn't change if the mass is larger. Because our friction force is going to be slightly higher, because our normal force is going to be twice as high. And our coefficient of friction remains unchanged. Now we'll see this changes a little bit here when we look at part 8, which would be what happens if we double the speed. And so if we're going from, let's find our original distance we would travel. which would be, let's see, mv squared over 2f, like frictional force. We're just going to use this as FF because we know there's no velocity component in this frictional force case, in this guy here at all. There's no velocity, so we're not going to worry about it. And so then we want to see what this d is if we double that velocity. And so we then get 1/2 m 2v squared is going to equal our ff times d. And we see that then this 2 gets cubed. And so we get the same answer, but with a 4 out front now. And so 4 times our original answer is just going to be a distance of 4d. It's a good lesson for any young drivers out there. If by doubling your speed, your stopping distance is quadrupled, which is less reaction time, which is less safe, right? More likely to get into accidents. So there's a reason why roads have speed limits. It is safer to stay within those because every little additional piece of velocity increases your stopping distance drastically by the square. And then number 9, we were like almost out of space, so let's hope we can do this without having to show too much work here. Number 9, a ball is thrown vertically upwards with some velocity v and initial kinetic energy ek. When halfway to the top of its flight, it has a velocity and kinetic energy, respectively, of which? So we expect if we're halfway to the top, at the very peak, all of our energy will be in mgh, right? This is going to be all in potential energy. At the very peak, there'll be no velocity. The ball briefly comes to rest before it accelerates downwards again. And so if we're halfway to that, that means we're at h/2. And this is all linear, so that means we have half of our energy is in potential energy. And so that means we expect our kinetic energy to be ek/2, so that rules out d, but that still leaves us with a, b, and c. The differences now would be what we expect our velocity to be. And so for an ek/2 to equal a 1/2 mv squared, so we want our, let's see, we want our new velocity, so let's call this vf, even though it's not the final velocity, this is the velocity at the halfway point. This is going to equal our initial kinetic energy divided by 2. And so we can multiply both sides by 2, divide both sides by m, and then we'll take a square root of both sides to get our final velocity, giving us v over the square root of 2, which is b here. Good. Any questions on those first few problems we got there? It's a little bit messy. I'll try to be better, but I mean, this was also 9 problems on a single page. In hindsight, maybe I should have split this up a little bit. I think in the future we'll see these next ones are a little bit, oh, yep, that was our work page. Yeah, this has got a little bit less going on per page now, so that's nice. We're also jumping around a little bit in the numbers here too. Don't worry about it. It's this is a curated set just to cover as many different ideas as we can and most relevant problems, just so we can spend our time efficiently here. So for questions 18 and 19, we're dealing with a ball swinging back and forth on a pendulum. Let's see. As point 2 is the lowest point in the path here. Point 3 is located half a meter above 2. Point 4 is 1 meter above 2. We're ignoring air resistance. So if the potential energy is 0.2, which we agree with, where will the kinetic and potential energies of the ball be equal? So that would be at point 3 here, right? Because at point 3, we're halfway up again. So we have half of our height. If we consider at the top being, like at 1 meter, being our full potential energy and no kinetic energy, which is what we expect that to be. So that means that we will reach our halfway point for our half of our energy will be potential, meaning the other half has to be kinetic, meaning they have to be equal. at point 3. And then the speed of the ball at point 2 is going to be most nearly what? Okay, and so that's going to be comparing our MGH, if we're starting from a height of 1 meter, to our 1/2 mv squared. We want to get our velocity on its own, so we'll divide both sides by mass, multiply both sides by 2, and take the square root, giving us v is equal to root 2gh. And this is actually a relation we'll see pretty often here. And that's going to be the square root of 2 times 9.8 times 1. Root 2 times 9.8 is 4.9. 3 looks pretty good, actually. 3 meters per second, but let's try this. 2 times 9.8 to the 1/2 power. Oh, I get 4.42. Oh, but I'm willing to bet they probably used 10. So let's double check that. Square root of 20 is 4.5. Okay, yep. So my broad strokes estimates of radicals isn't that great, but our mathematics was still accurate. My just first guess wasn't. Yeah, and so this approach is what we wanted to do. Just me eyeballing it wasn't as accurate as we would have hoped. Looking at 20, the figure shows a rough semicircular track whose ends are at a vertical height h. So we've got a little kind of half-pipe action here. A block placed at point P at one end of the track is released from rest and slides past the bottom of the track. Which of the following is true of the height to which the block rises on the other side of the track? Well, it says it's rough. So typically when they refer to rough surfaces, that means friction is not negligible. If we could completely ignore friction, if this were a frictionless surface, we would expect it to go up to h again. We don't expect it to go to 0 because we don't expect it to stop here. We've still got a lot of energy at the bottom here. This is kinetic energy. So we can get some height above 0, and it can go up to h. But we really don't know because it depends on how much energy the friction took out. How much work the friction did. Energy lost to friction, that's going to be option D. Cool, looks good. Graph shown represents the potential energy U as a function of displacement x for an object on the end of a spring, moving back and forth with an amplitude x0. Which of the following best represents the kinetic energy of the object as a function of x? So the kinetic energy we expect to be inverted. We expect this to be at the minimum when our x's are down here. We expect them to be zeros there, and at a maximum at, up here. And so the only one that fits that would be D. We can kind of have a look at the features we see here. We're going to be moving up, picking up our maximum speed at this point, and then slowing back down to 0, we then have 0 kinetic energy. And as we go back and forth between these, this has that sinusoidal motion that we expect of those simple harmonic problems. Again, we'll deal with these a little bit more in the future, but yeah, we can still use our conservation of energies on this. For 22, we've got a child pushes horizontally on a box of mass m, which moves with a constant speed v across a horizontal floor. Coefficient of friction is given as mu. What rate does the child do work on the box? So at what rate? Okay, so that's actually going to be a power calculation then. Which is fine, that works out well. So again, we're told constant speed. What do we expect when we see constant speed? That's right, acceleration of 0. Oops, what is this? That was a pad of sticky notes. And so let's kind of see what we've got going on here, right? So we've got a friction force slowing us down, and then the force that the child is applying. I guess let's call this one Fa for applied force. We'll call this one Ff for friction force. Looks good, looks good. And so the rate that the child does work on the box would be work over time, which is power. And so work over time is force times distance over time. But distance over time, that's just velocity. And we're given the velocity. And we know that the frictional force is going to equal mu mg. Because it's our normal force. We're on flat surface and there's no vertical forces offsetting us. So our normal force is equal to our gravity force, which is mg. And then we multiply by mu to make it a friction force. And then we get to multiply this by a distance, but we then have to divide by a time, and we don't know a time. But we know the velocity, which is distance over time. So instead of multiplying by distance, we'll just multiply by velocity, giving us option A as our best choice here. Good, good. Okay, so I'm going to grab a quick drink here. Excuse me. Oh, this wire is so persnickety. A block of mass 3 kilograms is hung from a spring, causing it to stretch 12 centimeters at equilibrium as shown. Okay. The 3 kilogram block is then replaced by a 4 kilogram block. The new block released from a position shown when the spring is unstretched. How far will the block fall before its direction is reversed? Okay. So we can use this first case to find our k value. This is going to be through Hooke's law. In the case of God, why does this? Okay, is the mic working now? It's working. Okay, thank you. So we have a downwards gravity force and an upward spring force when they are in equilibrium. We know, so that's going to be Fs, Fg. If they are in equilibrium, this means they are equal to each other, giving us that our mg is equal to our kx. We want to solve this for k. And so k is just going to equal our mass times gravity over x. Our x was 12 centimeters, which we probably want in meters actually, because we're going to then have this be in Newton meters. And so in this case, is this a good spot to write? Oh, close, yeah. So that's going to be 3 kilograms. I think we want to use 10 for g. Yeah, let's just use 10 for g. 10 meters per second squared over, yeah, so we do need this in meters because that's in meters. So 12 centimeters is 0.12 meters. So we have 30 divided by 0.12 for our k value, which is 250. Good, good. I don't want this. Okay, this is now echoing. Stop, stop, stop. Okay. Pulled up the calculator, pulled up the stream, made an echo. I apologize. So we've got a k value for our spring. This is newtons per meter. We want to find out how far will it fall before its direction is reversed. And so we know that so the block will drop to a maximum. So where's our equilibrium point? We're gonna go past this. Okay. If the spring is unstretched, how far will it fall before it's reset? So that's gonna be at the case when we have a maximum. All of our energy goes to potential energy. Oh, okay, yeah, and that's going to be a gravitational potential. So we're converting a gravitational potential energy into a spring potential energy on the bottom. At the top, we have some height that we're going to fall. And in this case, we also get that this is our x. right? Because the height we travel is the same distance that we're stretching the spring by. And so we want to solve this for x now that we know k. And for that, we can actually divide both sides by x to get this down to just to a linear equation. Multiply this by 2, divide it by k. So we get 2mg over k, which is going to equal 2 times 4 times 10, so 80 divided by 250, which is 8/25 of a meter. Let's see what that is. 8 divided by 25 is 3.32. So this is 0.32 meters or 32 centimeters. Let's see. Good, good. Oh, that one almost stumped me for a second there. But yeah, that wasn't too bad. Next we have, what is the kinetic energy of a satellite of mass m that orbits Earth of mass m in a circular orbit of radius r? We actually went through this before. Oh, did I drop a 1/2 term though? I might have dropped. I think I dropped the 1/2 term earlier. Yeah, that's gonna be our, because that's our potential energy that we're then shifting between. So that should be the 1/2 GMM over R. Not wildly confident on that one. But that has the right units that we're looking for. The only other thing is it could be B, and I don't see why it would go to 4. That's not wise. So 25, we've got a rock of mass m is thrown horizontally off of a building from a height h, as shown above. The speed of the rock as it leaves the thrower's hand at the edge of the building is v naught. What's the kinetic energy of the rock right before it hits the ground? Well, we pick up the potential energy that we drop of mgh, but then we have the initial kinetic energy that we're adding to it of m 1/2 mv naught squared. And so we combine these two, which would be addition. So we add these two terms together like that. So yeah, C was a good option, but it had a negative sign. And the other two just had the individual components, but it didn't have them added together. So D is going to be our choice here. Oh, I can barely read that. Okay, yeah, no, so we've got mass on a spring and a pendulum. It's simple harmonics all day today. So we've got a sphere of mass m1, which is attached to a spring, is displaced downwards from its equilibrium position as shown above, above left and released from rest. Sphere of mass m2, which is suspended from a string of length L, is displaced to the right as shown above and released from rest so that it swings a simple pendulum with a small amplitude. Assume both spheres undergo simple harmonic motion. Which of the following would be true for both spheres? So we've got maximum kinetic energy is attained as it passes through equilibrium position. That is a good choice. I think that's going to be it, but let's check all our other ones. We've got minimum gravitational potential energy is going to be as it passes through the equilibrium position. That's true for the pendulum, but not for the spring. So B is not true for both cases. The maximum gravitational potential energy is when it's at the point of release. That's not true for the spring either. That's true for this guy, not the spring. And then the maximum total energy is attained only as the sphere passes through its equilibrium position. That's also not true. It's going to be, the total energy is going to be constant the whole time, unless we have some outside forces. And so it was our first choice, which we thought A is the correct one. Our maximum kinetic energy is as we're moving through equilibrium, which is what we saw in those previous problems, right? When we had the 1/2 kx squared equal 1/2 mv squared. And then for the pendulum case, that would be mgh is equal to 1/2 mv squared, where we also wrote this as 1/2 mg. Ooh, I don't want that there. I want this L times 1 minus cosine. That was one of the previous problems we saw. Again, we still expect that's our maximum potential energy. This is our maximum kinetic energy when potential is 0, going through the equilibrium. Yes. Yeah, okay. Hmm. I'm second guessing myself. No, that's not the minimum. Okay, yeah, so that's good. That's fine. I am not thrilled with the equilibrium being above this, but that's fine. I don't want to. That's I've every other choice we ruled out for good reason. So we're gonna go with that pragmatism. Hi there. So we've got we're pulling problems from it's an MIT set of um, just of old AP multiple choice and FRQs. And so these ones have been kind of curated for just focusing on work, power, and energy. So yeah, so we're taking a look again. This is the largest unit on the AP test, so we've got a slightly longer setup for today, but it's all good. Yeah, and so next we've got a spring-loaded gun that can fire projectile to some height h if it is fired straight up. So if the same gun is pointed at an angle of 45 degrees from the vertical, what maximum height can now be reached by the projectile? Um, okay, so this is a case of us converting a spring potential into a kinetic energy into a height. And so if the spring is unchanged, the velocity that we launch out of will also be unchanged. The only difference is now we're introducing a 45 degree, and so instead of having this is kind of more of a kinematics problem actually. Instead of having all of our uh, vector go upwards, is that blocking? Oh, I'm blocking this. So this is equal to mgh at the top. But so instead of having all of our velocity go upwards, now all of our velocity is going this way. There's only an upwards component. And we can relate these to being, for a 45-degree angle, will be 1 square root of 2. Uh, and so we would expect then the height, if we then brought this down to be our standard, would have to divide this, would divide every term by square root of 2 to normalize it. So we divide that by square root of 2, divide that by square root of 2, divide this by square root of 2, making this go to 1. That's the same as our original velocity. Our upwards component is that component divided by the square root of 2, giving that height here. Ooh. Okay, no, but hang on. And so then so that's our launch velocity, though. Okay, hang on. I'm not confident in that yet. Because that's our launch velocity is going to be b over root 2 in the upwards direction. And if we square that, that actually gives us half of the height. Okay, yeah, so I originally didn't like the look of this one. It seemed a little too simple. But no, when we square the velocity, we do get a 1 over 2 term for both of these, which is kind of blocked by my face. I apologize. Yeah, and so it's actually then going to be C here. 35, we've got an ideal massless spring is fixed to the wall at one end as shown. A block of mass M is attached to the other end of the spring, oscillates with some amplitude A. Lots of masses on springs today. They're really going for those. Force constant on the spring is going to be given as which? So we know it's... God, why does that keep doing that? Okay. Well, so we know our velocity, right? And so that velocity is going to be at this maximum point. This wire needs to chill. There we go. Our maximum kinetic energy is going to equal our maximum spring potential. And that's going to be when we displace our spring by some amplitude A. We want to just take this relation and solve it for K. And so we're just going to multiply both sides by 2 and divide both sides by a squared, giving us mv squared over a squared. We could even factor out the squared for v over a if we wanted, but don't really care. Yeah, and that's going to be C here. there. The other ones just have a 2 and a G. We don't really want any of those. What's the difference between? Oh, that's yeah, it's a 2A. Yep. Okay, looks good. Cool. Alrighty, alrighty. Next we've got person pushes a block of mass 6 kilograms with a constant speed of 5 meters per second straight up a flat surface inclined 30 degrees above the horizontal. Constant speed. What does constant speed tell us? Zero acceleration. The coefficient of friction between the surface is given as 0.4. What is the net force acting on the block? Again, constant speed, zero acceleration. The net force is going to be 0. We've got lots of forces acting on us in multiple directions here, but if they're all balanced, we expect our motion to be constant, which is what we're given here. So they're all balanced out. Every force has an equal and opposite force or component, giving us a net force of 0 acting on this. Yeah, they gave us a lot of numbers here. I think they wanted us to try do a calculation and waste our time, but we can bypass that, which is nice. Next we've got a block of mass M on a horizontal surface is on a massless spring. Yep, mass on a spring again, everybody. The block is pulled some distance x from the equilibrium and then released from rest, moves towards the equilibrium. What coefficient of friction between the surface and the block would allow the block to return to equilibrium and stop? That's kind of a good question, actually. So we want to get to the point where when we travel some distance x, because that's the x that returns us to the equilibrium, all of our potential energy is siphoned away. So we get 1/2 kx squared is going to equal our force of friction times the distance that we would travel, and that distance would be x. And so we can divide both sides by x. And then we'll unpack this force of friction a little bit here. That's going to be mu times mg. And we want to solve for mu in terms of x, so we'll just divide by m times g, giving us mu is equal to kx over 2mg. And that is c. Notice how it's not kx squared. A looks kind of promising, but we divided out one of the x's because this is the work done by friction. So we're traveling a distance x as we go. 38, we've got an object is dropped from rest from a certain height, ignoring air resistance. After a falling distance d, the object's kinetic energy is going to be proportional to which of the following? Well, it's going to be proportional to d, because as we are falling, we are traveling down some height, or we're traveling down some distance, I suppose. We'll use d. And that's potential energy being lost, right? So at some height here, right, if our starting potential is mgh, our final potential would be mgh minus d. So we're linearly taking this away, and that would be in parentheses. Is that off the side? That is off the side. Ugh, I'm sorry, I cropped this window a little bit badly there. Yeah, and that would be, yeah, and so then our kinetic energy is then going to be rising linearly as this d increases linearly. As our distance gets further and further away, this energy that's being pulled out of potential energy has to go somewhere. It's not going into air resistance, it's going into kinetic. So kinetic energy is growing proportionally to d, which is option D, which is nice. So our last one for this page here, I think this actually might be our last multiple choice one for tonight. We've got an object is projected vertically upward from ground level. It rises to some maximum height h. If air resistance is negligible, which of the following must be true for the object when it's at a height h over 2? Its speed is going to be half of its initial speed. That's not going to be the case, because we expect the kinetic energy to be half of that, and so its speed would be then lower than that, because that needs to be a v squared term. Its kinetic energy is half of its kinetic energy. its kinetic energy at the height h over 2 is half of its initial kinetic energy. Yeah, we do expect that to be true because we are at half of our maximum potential energy. So half of our energy is just somewhere that's going to be in kinetic energy. Potential energy is half of its initial potential energy. Ooh, C is really close to being right. But C, the initial potential energy is 0 because we're starting on the ground from ground level. So half of 0 is 0. We don't expect it to be 0. It's half of its maximum, but that's not the initial. And then the total mechanical energy is half of its initial value. No, that's also false because we expect the total mechanical energy to be equal if we are ignoring air resistance. So B, we were correct to think B was the right choice here. Good, good. Any questions on that so far? Looks good, looks good. Let's move on to some FRQs here. So we've got a little roller coaster action going on here. We've got a designer's working on a new roller coaster, and she begins by making a scale model. On this model, a car of total mass 0.5 kilograms moves with negligible friction along the track shown in the figure above. We've got a kind of sinusoidal curve going up around the upper side of this little circle here. Cars starts out with an initial speed V0 of 1.5 meters per second. At the top of the first hill of height 2 meters. Point A, located across, the height is 1.9 meters in the upper part of the circular arc, which is 0.95 meters. Cool. So we want to calculate the speed of the car at point A. And to do that, we'll work out the kinetic energy at that time. So the kinetic energy at that time is some 1/2 mv squared. We want to find this v. That's going to be equal to the energy that we kind of put into the system, right? We can technically add, in fact, actually, this is probably a better way to show this. Let's add also the height at this time. I'm going to call this h2. So this is our total energy at this time. We do have some potential energy above the ground here. And then in the beginning, we have some initial potential energy. This h1 is our 2 meters. And then we also have an initial kinetic energy due to that V0 that we were given. And so we can bring this to the other side. And so this gives us 1/2 mv squared is equal to, I can factor out the mg, giving us h1 minus h2. Incidentally, this is where I would have started before, but I figured we'd show this intro step as we went. Plus this initial piece of kinetic energy. We want to get V on its own, so we're going to divide all sides by mass, but there's mass in every term, so it all cancels, which is nice. And then we'll multiply by 2. We'll get a 2 here and cancel the 1/2 there. And then we'll take the square root, giving us a velocity of root 2g h1 minus h2. This is just that difference in height, or 0.1 meter. It's 0.1 meters, excuse me, plus our v0 squared. And that's going to be 2 times, I think, are we meant to use 10 for g? It doesn't mention it, so I'm just going to use 9.8. 9.8 times, and our height difference was 0.1 meters. That's 2 minus 1.9. And then we also have that V0 squared term, which is 1.5 squared. And let's make sure these are all in the same thing. Good, good. That they are, giving us a final velocity, or velocity at point A, of 2.05. I'm actually going to label that as VA. And that's meters per second. So a little bit faster than 1.5. But again, we're at the top of a hill, so we kind of expect this to be pretty comparable. On the figure below, draw and label vectors to represent the forces on the car at point A. So at point A, I mean, we're just sitting on a track. There's nothing propelling us, so we really just have a normal force pulling us upwards and a gravity force pulling us downwards. Calculate the magnitude of the force of the track on the car. So track on the car, that's going to be the normal force at point A. Yeah, so I mean, so that looks like that's going to be a centripetal force problem. So we expect our, because we're moving about a circle, or the edge of a circle, we expect our centripetal force to equal Fg minus Fn. And that's going to equal mv squared over r. Do we have the mass? We are given the mass. Okay, good. And so we can take this relationship, because these are all things that we know, and use it to solve for Fn. So we'll add Fn to both sides, we'll minus mv squared from both sides. We're going to invoke the definition of Fg. So we write this as mg minus mv squared over r is equal to our normal force, the force acting on this object, which is 0.5 times 9.8 minus 0.5 times our velocity, which was 2.05 meters per second. We're going to square that, and then we'll divide it by our radius, which is 0.95 meters. Good, good. Plugging that into a calculator, we've got I want to divide this by 0.95, just getting all our terms here, and I want to make sure that I'm also getting my parentheses correctly here. And this gives us a normal force of 2, oh, that's like off the edge, isn't it? Okay, I'll write this somewhere better. A normal force of 2.68 newtons. 6.9 if we round. Let's round. 2.69 newtons. Good, good. Yeah, so that's for part C there. Part D, in order to stop the car at point A, some friction must be introduced. Calculate the work that must be done by the friction force in order to stop the car at point A. Well, that's just going to equal the kinetic energy at point A, which we can calculate. The work that must be done to stop it has to be equal to this kinetic energy at A, because we need to bring that kinetic energy to 0 for it to come to rest. We need the velocity to go to 0, and that's the only way kinetic energy goes to 0 without the mass going to 0. Which we know all the things for that. That's just going to be 1/2 times 0.5 for our mass, times our velocity at A squared, which is 2.05 squared. And that gives us a work necessary of just 1.05 joules. This is the work done, so that's not too difficult. Now E asks, explain how to modify the track design to cause the car to lose contact with the track at point A before descending down the track. So for this to lose contact, that means our Fn has to go to 0, meaning we have to be coming in at a faster velocity. Fn goes to 0, so we have to raise, I mean, we could actually do the numbers for this. I don't think so this is just to kind of explain, so I don't think they want us to do the actual calculation, but what we could do is we could raise the initial height, how much space do I have to write? Okay, not too bad. Such that, such that our velocity at this point, mv squared over r, is greater than or equal to mg at point A. And that would then give us the case where if this is then greater than that, this subtracts this down, making this whole term go to 0, which is what we want. Oh yeah, so I guess the other way we could also do that, because we want to raise this, is we could reduce the radius. But that would also then increase the velocity, so you'd have to scale that. Raising the initial height would be easier, but probably more cost prohibitive because you're adding material. If you're subtracting material, in theory, that makes your design cheaper. So reducing the radius is another good option. You'd have to then justify that, though, as trying to solve for the case where our normal force goes to 0. This is the condition that we have to satisfy. Any questions on that so far? Looks good, looks good. Let's move on to the next one then. Okay, so we've got a small block of mass m released from the top of a curved frictionless ramp shown above. The block slides down the ramp and is moving with a speed of 3.5 v naught when it collides with a larger block here. So we're kind of coming down, and then we hit this block when we're traveling at 3.5 there, and then this flies away at a speed of 2v. Oh, that's kind of cool when it fades like that. Okay, I'll stop getting distracted though. So determine your answers to the following questions in terms of quantities, given quantities, fundamental constants. So I believe that's going to be our m and our v naughts. These are our quantities that we can use. Do we know h? Oh no, we're to determine h. Okay, so yeah, I mean, determine the height from which the small block was released. In the beginning, all of the energy was in potential energy, excuse me, with the mass of big M times our acceleration due to gravity times h. And at the end, we're traveling with a kinetic energy, because we're traveling at a speed of 3.5 v naught. And so that gives us a kinetic energy of 1/2 m times 3.5 v naught squared. Excuse me. Yeah, and then this is the relation we just want to solve for h here. So we'll divide both sides by mass, and then we'll divide both sides by g, giving us a velocity of 3.5 squared times v naught squared over 2g. We could simplify that if we wanted to, but I don't really want to, so I'm not gonna. Again, you don't lose points for not simplifying, but you do lose points for simplifying incorrectly. So most of the time, it's not worth the risk. The only time that you are expected to simplify, it would be if they ask you to show a value. They're trying to say, show that this value equals this value. Therefore, you have to go through all the steps to simplify it down to get it into the form that they are looking for. But they will specifically mention that in the problem. If not, don't bother with it. Don't risk it, unless you feel really confident with your algebra and you've got some time to spare. B asks us, the larger block slides a distance d before coming to a rest. Determine the value of the coefficient of kinetic friction. Okay, so I mean, this would have been an actually difficult problem if they made us do calculations about the collision. This is actually really simple because we're given the speed after the collision. So we know the kinetic energy that this block has when it starts moving. This larger block starts traveling with a kinetic energy of 1/2 times 1.5 m, and then our v is 2v naught squared. And then this is going to equal, for all this energy to get siphoned away by friction, this has to be work done by the force of friction. So that's going to be the force of friction, mu times our normal force. We're on flat ground at this point, so our normal force is equal to our gravity force, times that distance d, which is going to be one of those values we can use. And so we want to take this relation. Oh, I guess I did miss something though, because our m is really this 1.5 m. Yeah, and so we want to solve this for mu. So we'll start by dividing both sides by 1.5 m. And then we'll just divide both sides by GD. So giving us, I'll simplify that because I can do 2 squared in my head. 4v naught squared over 2 times g times d, which, yeah, we can simplify then. 4 over 2, that's pretty straightforward. 2v naught squared over gd. That is going to be the coefficient of friction necessary to bring us down inside of a distance d from an initial speed of 2v naught. Yeah, any questions on that so far? Looks good. All right, cool. Okay, so we've got a twofer here. And I think this is our last pair. We're doing pretty good. We're making good time here. Let's focus on the top one here. And if we run out of space, we'll do the second one on a new page. Both of which look fairly short though, so we should be okay. First one, we've got a pendulum consisting of a small heavy ball of mass m at the end of a string of length L. So that's this little L there. They use the little swoopy L. Is released from a horizontal position. When the ball is at point P, so down at this point here, the string forms some angle theta with the horizontal. In the space below, draw a force diagram showing all the forces acting on the ball at point P. Well, that's easy. At point P, there's only 2 forces acting on us. We have our force of gravity, as usual. That's going to be pointing straight down. And then we also have a tension force. This is the tension in the spring. Not spring, the string. And that's going to be pointing along the length of the string at this angle theta. So next we want to determine the speed of the ball at P. So that does use a centripetal thing, but I think we use the centripetal to solve for C. So we have to use this based on the distance that we've traveled down here. Yeah, so we want to determine this height, and then we can get this from mgh is equal to 1/2 mv squared. Again, then this relation just comes to v is equal to root 2gh, but we need to determine h in terms of L and theta. And my first instinct just says use L sine theta, and it's probably not that. So let's not do that. So this is going to be... Okay, so that comes in there. Does that make a perpendicular if we do that? Okay, well, here's what we can do. We can make... This is probably not the smartest way to do this, but we can make an isosceles triangle and divide this down the middle here. Now we have a pair of right triangles with a hypotenuse of L each, and they're enclosed by an angle theta over 2. And then the H, we need to get this top angle here. Oh, but we know this, so this upper angle, let me label it, not in red, we used red already. Let's label it in green here. So this upper angle, let's call that alpha. Alpha plus theta over 2 has to equal 90 degrees because these two are, they make up the 2 other angles of a right triangle, and the sum of all angles in a right triangle is 90 degrees. And then this total angle here also makes 90 degrees here, meaning that this angle in the top here has to be theta over 2. So we've got 2 triangles that we're interested in. We've got some, we've got this one on the left here that's enclosed by H and has a theta over 2 on the top. And then we've got this, this right triangle coming from the isosceles that has theta over 2 up here, has a side length of L, and we want to get this side because we know the hypotenuse here if we call this side x, this hypotenuse of this guy is 2x. And so we then can connect these two. So this is L times the sine, because that's opposite over hypotenuse. So the sine of theta over 2 gives us x over L, giving us that x is equal to L sine theta over 2. And then h is the cosine relation, because the cosine of theta over 2 is going to equal h over 2x. H over 2x, solving for h gives us 2x times the cosine of theta, of theta over 2. Oh, this is going to work out quite nicely with a little trig action here. Because our x now is L sine theta, so we now have our h as 2L sine of theta over 2. Oh, that's like kind of missing an I there. There we go. Times the cosine of theta over 2. Now, can anyone spot the trig identity? It's not an obvious one. This is going to be the double angle theorem, I believe. Basically, we expect 2 sine. How do we want to write this? Let's write the identity first. Would be 2 sine cosine is equal to the sine of twice the angle. And we have that in here, right? Our x is theta over 2. So we can pull this out to say this whole term is equal to, pull out the 2, pull out the sine, pull out the cosine. This just gives us L sine theta. Okay, so that was probably a way better way of doing that then. Because that's a really simple result. But that's okay. That's kind of neat. I always like taking different routes when you can. It's good to test that different methods work. It shows that they're consistent. Yeah, did I get that right around? Yeah, that's the right way around. Good. And so that's our h, meaning then our velocity all the way back up here is going to equal square root of 2gl sine theta. Good. So that's the speed of our ball at that point there. Next, we want to determine the tension in the spring or in the string. Okay, and that's going to be. I guess we want to break up gravity into two components here. To start with, let's take a piece coming down here and going across here. And then our theta would be in the top here. And so this x component of gravity is going to be part of our centripetal force. That's going to be this side there. And so we can say Ft minus Fgx is going to equal mv squared over r. And our Fgx is going to equal okay. Let's bring this down here. We'll do the next one on the next page. And so this gives us Ft is equal to mv squared over r plus Fgx. Now this Fgx, that's the sine relation, so we're going to write that as mg sine of theta, using the same moves that we've used up here. And yeah, that we can calculate, because this r is L, this v is v squared is 2gl sine theta. We can factor out an m. Yeah, so our Ft, let's factor out that m. Our v squared is 2gl sine theta over L plus g sine theta. I can cancel the L's. Can leave it like that if we want. But this is really not that difficult, because that is just 2g sine theta plus g sine theta. That's 3g sine theta. So our Ft is equal to 3mg sine of our angle theta. Good. Any questions on how we set that up or how we did any of the different parts here? Kind of a little complicated towards the end there. A lot of centripetal stuff going on. I think there might have been a better approach to that the triangle step there, but our method worked out quite nicely, so I'm happy with that. Okay, so let's take a look at this next one, but I'm going to make us a new page. Can I bring this over, or is this going to really not like that? Oh, it's not great, but we can still bring it through. This one here. There we are. Okay, let's make that a little bigger. So now, in fact, I can even move this up so we don't see the top one because we've done the top one. There we go. Can you see that on the screen? Good, good. All right, so we've got a single parter. That's nice. Ski lift carries skiers along a 600-meter slope inclined at 30 degrees. So that's our distance. There's our angle. To lift a single rider, it is necessary to move 70 kilograms of mass to the top of the lift. Under maximum load conditions, 6 riders per minute arrive at the top. 60% of the energy supplied by the motor goes to overcoming friction. What average power must the motor supply? Okay, well, let's think about how high we have to lift these guys. Because the work we do by raising the potential energy of each rider, is that for a single? Oh, 6 riders per minute. Okay, cool. I was wondering if we were looking for a single rider, but no, we have another condition we're going to add later. This is actually kind of cool. There's lots of different conditions we have to meet here, but it's really just a single calculation. So our height is then going to be our hypotenuse. So the sine relation of 30 degrees gives us our opposite over our hypotenuse. So 600 times the sine of 30 equals h, which is, it should be 300 meters, I believe. Quietly double check that. Yep, 300 meters. So we're trying to raise a single person up 300 meters. So for each, so let's see, we want the work per person. Let's not use P for that because P is going to be power. I mean, I can just write person. So the work per person is going to be mgh. So that's going to be, our mass is 70 kilograms times g. Let's use 9.8. Times 300 meters. And this isn't going to be meters per second squared. I just forgot to write it. That's okay. And this gives us a value of 700 times 300, about 21,000 maybe? Ballpark? 300 times 70 times 9.8. Less than 21,000. In fact, well, no, higher than that because I was off by an order of magnitude. Be 21 times 10,000. But it's reduced a bit because we use 9.8. And that's joules per person that we need. So we want to then we then need 6 people per minute. So we want to multiply this. This is joules per person times 6 person per minute. And we want, if we get it in joules per seconds, that's in units of watts, which is what we want to kind of work with. So we're going to get one more conversion factor, which will be, we want that on the bottom. So we have 1 minute per 60 seconds. Minutes cancel out. We have joules per second now. And so we just divide this by 10, actually, because we multiply by 6, but then divide by 60, giving us then, we expect, without friction, except for the comma goes back one place, doesn't it? 20,580 watts, and that is without friction. And so if 60% of the energy goes to overcoming friction, means this has to be 40% of our energy. So we can use related rates here, right? So we can say our fraction. How much space do I have down here? Can I write over here? Yeah, we'll have enough space over here. So this fraction, 2,580 per my total. Let's call this P. This is going to be the total power needed. Is going to equal the proportion of 60%. Oh, sorry, of 40%, right? Because 60% is going away. So I want this to equal 4 out of 10. It's just a nice fraction way to express 40%. We'll just cross multiply this then, right? And so we get, again, multiplying this by 10, bringing this back out to this guy, it's going to equal 4 times the power we need, giving us the total power is going to equal this divided by 4. This 5,800 divided by 4, giving us a nice power of 51,450. And that's going to be in watts. And that will be our final answer here. Notice how we didn't actually calculate the work done by friction. We just calculated the total power we would need per person, and then used that related rate by knowing that 60% of this was just not going to affect the motion of the skiers. And so this we then just designed a version that had 60% excessive power. And I guess to verify this, then we'll take 40% of our final answer times 0.4. It's the same version. Yep, it's the same operation. Good. And so that was actually the only power problem we worked with today, but that's fine because yeah, we're not going to see too many of those, I suppose. Yeah. So that's about all we have for today here. This was work, power, and energy. Once again, you can check us out at 314education.com. We've got online tutoring we can do remotely. You can follow us on Instagram. We're at 314education. We might be doing some giveaways soon, as soon as we can 3D print them. And then next Sunday we'll be doing this again, moving through again. We have an 8-part series going through every unit until the last one, which will be the day before. We're just going to go over everything, just run through general strategies, all the different equations and relationships that we've picked up, and how to manipulate those and use those in context to solve for answers that you need. Good, yeah, and I think that's all we have to announce. So thank you everybody for tuning in, and until the next time, you take care, keep safe, and I'll see you guys